Hello, today let's try to evaluate an integral using Green's theorem, right? So let's start. Use Green's theorem to evaluate integral closed under the curve C x y dx plus x square y cube dx, where C is a triangle with vertices 0, 0, 1, 0 and 1, 2 with positive orientation. Right? So let's try to solve. Here it's given to evaluate this integral xy dx plus x cube y cube dx using Green's theorem, and the closed curve is a triangle with the given vertices. So let's try to plot this triangle here. So let's draw the coordinate axis first. This as x-axis and this as y-axis. Here it's given the origin, right, 1, 0, which lies on x-axis. This point, let it be 1, 0, and it's 1, 2, right? 1 and 2, let it be here. This point 1, 2, this, right? And it's given the curve is having a positive orientation. So let's draw this, right? Then this region is, this region is R. Let's call it R, right? And as you can see, the P is P is xy and Q is x square y cube. They have partial differentials, right? So let's try to calculate. First, write the equation. We know the Green's equation. P dx plus Q dy is double integral over the region R dou Q by dou x minus dou P by dou y dx dy. Fine. And you can see there is a partial first order differential for both P and Q, which are function of x and y. So let's proceed with these, satisfy these conditions. So now we can use these formulas here. Here, let's try to do this here. P is xy, right? Q is x square y cube. Fine. Then dou Q by dou x is 2x y cube. Dou P by dou y is x, right? Then the integral which was asked xy dx, sorry, xy dx plus x square y cube dy is double integral over this region R. Dou Q by dou x is 2x y cube minus dou P by dou y is x into dA, right? So we need to calculate the integration limits. What about the integration limits which satisfy this region, triangular region, right, which covers the whole region of triangle? So as you can see here in this graph, x varies from 0 to 1. What about y? Here y, as you can see, y is a function of x, right? What is the line equation of this, I mean the hypotenuse part. The hypotenuse is y equal to mx, right? The slope of this equation is, sorry, the first slope of this line is 2 minus 0 by 1 minus 0 into x, as there is no y-intercept because it's passing through an origin. Then this is y equal to 2x. The equation of this line is y equal to 2x, right? Then integration limits for y is, y varies from 0 to 2x, right? As you can see, this from this origin, y varies from y to 2x. That means it is related to x, right? Then this can be written as double integral x varies from 0 to 1, y varies from 0 to 2x, 2x y cube minus x into dy dx. Fine. Now let's calculate this part first. Y part. Here it's x equal to 0 to 1. As we are calculating with respect to y, this will be 2x into y power 4 by 4 minus x into y. Right? And the integration limits are 0 to 2x dx. Fine. This is 2 ones, 2 twos. This is integral 0 to 1 x by 2 into y power 4. Y is, the upper limit is 2x whole power 4, and if you substitute the lower limit y equals 0, it will not contribute. Then minus x into y is 2x, and similarly here y equal to 0 will not contribute, so dx. Fine. This is integral 0 to 1 x by 2 into 2 power 4 is 16, x power 5 minus 2x square dx. Fine. 2 ones, 2 8. This will be integral 0 to 1. Sorry, this is x power 4, right? And this is 8 x power 5 minus 2x square dx. So finally this will be 8 into x power 6 by 6 minus 2 x cube by 3. For whole this case, integration limits are 0 to 1. Right? This will be 2 4s, 2 3s. Then this is 4 by 3 into 1 power 6 minus 2 power 6 is 1 minus 2 by 3. Then this is 2 by 3. So finally, integration of this along closed curve xy dx plus x square y cube dy is 2 by 3. Fine. Now let's calculate the second question. Question 2. Similarly here, evaluate integral along closed curve y cube dx minus x cube dy, where C is positively oriented circle of radius 2 centered at the origin. Alright. Here, which is given is it's centered at the origin and it's of radius 2, and this is the region, right? This is x, this is y, right? Here, see, here it is p equal to, here just write the formula again here, integral along closed curve p dx plus q dy is double integral over region R this is region R, dou q by dou x minus dou p by dou y into dx dy. Fine. As you can see here, the p is here, p is y cube, q is minus x cube. Both are having the first partial derivative along this, I mean this region R, which is a circle here whose center is origin and the radius of 2. Fine. So let's proceed this integral along closed curve y cube dx minus x cube dy is along this region R, which is a circle. Fine. Then dou q by dou x, right? Dou q by dou x is minus 3x square, minus 3x square. Dou p by dou y is minus 3y square, minus 3y square dA. Fine. You can bring the minus 3 as common and out of the integral, then this will be over this integral region R x square plus y square into d. As it is a circle, so it's better to figure out the area using polar coordinates, right? Using polar coordinates, we know that x is r cos theta and y is r sin theta, dA is r dr d theta, right? Here x square plus y square is r square, right? Then this becomes minus 3 into, as it is covering the full circle, theta ranges from 0 to 2 pi and r value ranges from 0 to 2 because the radius r is 2, right? Then this will be r square, x square plus y square is r square, dA is into r dr d theta. This will be minus 3 into d theta. If you integrate it, it will be 2 pi, right? Then this is r cube. R cube integral is r power 4 by 4. These are 0 to 2. Then this is, let's try to simplify this. This will be minus 6 pi by 4 into 2 power 4. Fine. This is 2 2's, 2 3's, minus 3 pi into this is 2 1's, 2 cubes. 2 cube is 8, 8 3 are 24. So this will be minus 24 pi. Right? Finally, integral along closed curve y cube dx minus x cube dy is minus 24 pi, where C is a circle of centered origin and